done in, okay. Thank you for recording the session. One of the fundamental tasks that we do in machine learning, and I would take us through some slides quickly. Hopefully some of you have some background on what I'll be seeing. Some of it will be like revision to what you've discussed with Dr. Shamsuddin. I just want to reiterate so that you don't get confused if I by some of the things that I'll be doing. So we start with this will be very quick. What is machine learning? We know humans learn with experience. Whatever you go through in your daily lives, you learn from that, and that is how humans learn. On the other hand, machine learn from data, not from experience, and that's why when we are doing machine learning, we talk about data all the time because that's how we do machine learning. So there are many things that we do that we consider machine learning. I wouldn't take too much time. When you receive your email, sometimes Gmail automatically sends some to your spam box. How does it know they are spam? It's mostly using machine learning. When you are watching your Facebook, you get videos. How does it know which video to send to you to watch, which one interests you? You'll be interested that it normally shows videos that you like, your interest. It uses some of your data to do that. All of those and many other things. And this is a very big, general architecture of the machine learning process, how it works. You have your data, then you pre-process it. You've done a bit of data pre-processing. You know what that is? Preparing your data so that it's in a good form. Then you apply some machine learning algorithms. Maybe you apply 2, 3 to see which one is the best. You get your best model, and then you use that model for your application. So we have two types of machine learning. What we call supervised learning and unsupervised. Don't forget to mute yourself when joining us. We have what we call supervised learning and unsupervised learning. Um, for now, we're looking at supervised learning. So we look at what that supervised learning is. So normally I give students example of when you want to teach mathematics. How do you do that? You go to the board as a teacher and then you give students examples. Let's see 5 examples. 2 plus 2 equals 4, 2 plus 3 equals 5, and all of that addition. So you give them examples, you teach them, they look at the examples and the answers. Then when you want to test them to see whether they understand or not, you give them questions. But whenever you give them questions, you already have your marking scheme. You know the answers to the questions. So the students try to put in the answer. So when any student brings the answer, you compare what he answered and the answers that you already know, and then you determine how much he gets, 4/5, whatever, based on that. So this is generally how supervised learning works, whereby you give the machine a number of tasks and the answers. So the machine tries to look at the questions and the answers to learn how to solve that problem subsequently. So this is how supervised learning works. So you know the answers. For example, we have generally two, I don't know if I have this in the slides. We generally have generally have two categories of supervised learning, which is the regression problem and the classification problem. So let's look at the classification problem is because it's sometimes easier to understand. You have balls in a basket of different colors, red, brown, green, and all of that. And then you want to determine which one is red and which one is brown of the color. You want to separate them. That's a classification problem. So when you want to do this, for example, with machine learning, you need to give the machine learning algorithms for the computer the balls, their properties. What are the properties of red ball? What are the properties of blue ball? What are properties of all balls? And then the actual color of it. So it looks at these properties and it looks at the answer, and then it learns from that. So this is what happened in classification. So that is classification. So when we are trying to predict our output that is in distinct classes, like colors, like gender, whether a person is based on his properties, let's say his height, weight, body mass index, and other things, you predict whether a child is a boy or a girl. There's nothing in between. So this is classification problem. So regression, it's similar, but the only difference is using those properties, you want to predict a continuous. For example, you want to predict the age of a person based on some features. Age can be 22, can be 23, can be 22.5 point whatever. So there is no distant classes. That's why we don't have classes. The moment you hear classes, it's classification problem. We have distinct, they are finite. Even if there are 1 million different classes, they are still classes, they are distinct. But regression problem, normally we are predicting continuous number like age, price of a commodity, interest rates, and all of that. So we have many different kind of algorithms. We have the most fundamental linear regression, neural networks, about vector machine, KNN, Bayesian, and all of that. I don't know how much of this you've done with, how much of introduction you've done with Shamsuddin. I don't want to take too much time. This slide will be given to, I've already shared it with Bala, so you can go over it. It's quite straightforward. This is a classification problem when you want to classify fruits into distinct classes, whether it's apple, mango, banana, and all of that. You have to give the machine learning the properties and then the label. Whenever you have a label, then that's a classification problem. Okay. Any question about this? I'll stop sharing my screen. Any question, or can we proceed? It's very easy, right? Okay. So I will take us into a bit of more technical component. Bear with me if you don't, we'll do a bit of mathematics today. Bear with me if you didn't get everything. You will have the slide and you'll have time to go over it on your own. And if you have questions, you can always ask. So we've seen, okay, how do I play this? This slide also will be shared to you by Abala. I give it to him, but I don't know which version. So we've looked at a recap of introduction to machine learning that you've done with Shamsuddin, even though I use a different material. Um, Now I can assume you can tell me what supervised learning is and what unsupervised learning is, and then a bit of generally how it works. So now I will take us over some of the algorithms we use and the general architecture. It's a bit of mathematics, so please bear with me. So first we'll start with KNN. After KNN, We'll start with linear models, and that's where I will focus and discuss more about linear regression and where most of the maths will come from. You don't have to understand the full of it. You just need to know what the concept is behind. All the things that you'll be seeing will be done by computer, so you don't need to do any of the mathematics yourself. And if you have studied mathematics or statistics, it's very easy. For those not from mathematics background, may be a bit more difficult for you to get it. So for Canon, key nearest neighbor is arguably one of the simplest machine learning algorithms. Building a model with Canon only involves storing the data set. That's all it does. Unlike what happens in information machine learning, to make a prediction for a new data point, whatever we have, in the supervised learning, um, excuse me a bit. Um, we have our data, we learn the parameters, we'll see what are those parameters, and then we make a prediction. KNN doesn't work that way. It just shows the entire data set. So to make a prediction, the algorithms find the closest data points in the training to its nearest neighbor. So it already have data points, the training data, meaning the futures and the class, right? So what it does is it just try to find, if you want to predict a value of y, it just looks at what is closest to that value and then pick the closest to that value. So that's what happens. It's not really learning. So the algorithm is instant-based learning, meaning we don't learn the weight from training data to predict output as in model-based algorithms. All other algorithms that will be used are model-based, but use the entire training instances to predict the output of unseen data. It is lazy learning, meaning the moment the model is not learned using training data prior. Instead, learning process is delayed until when you want to make a new prediction. And then it's non-parametric, meaning KNN, there is no predefined form of mapping function because it's not a model actually. It's instant-based, so you don't have any mapping function. So this is how key I will escape so that I will be able to move my mouse. So this is how KNN works. We have the red triangles, they are training. Class one, we have two classes here. The triangles, a red, and the cycle blues is the second class. Let's say 0. So we have these classes. So what KNN does is, if we want to make a prediction for with star, this red and blue star, please mute yourself if you are typing. This red and blue star are our tests, what we want to find out, what we want to determine. The blue star is for blue class, for this class, and then so what it does is it just find the nearest to it, which is the nearest. It's close to this star is closest to the cycle, so it just says it's a cycle. This star is closest to a triangle, it says it's a triangle. So this is what happens when we have k as 1. However, this is not ideal. Normally we don't pick k, we don't pick only one neighbor. This is when we are considering one neighbor. Generally, we want to consider more than one neighbor because, as we have seen, it's not all in some instances the closest neighbor may not be the class that you want to predict. So you pick a number of neighbors and then you find you can do any scoring, let's say majority vote, to find which neighbors have more. Here we have, this is the value we want to predict, right? And then among the neighbors, the closest neighbor is a cycle, but we have other neighbors that are triangle. So you see, if we pick a cycle, we are classifying this because it's actually a triangle. But if we use k equals to 3, then it has more neighbors as triangle. So we will most likely pick triangle as the appropriate class. This is when this is when we pick more than one nearest neighbor, and that is what our K is standing for here, the number of neighbors that we consider. So we normally consider more than one, we always consider more than one neighbor, and then to do that. So there are ways of we will look at this algorithm more thoroughly. There are many ways we use to determine the appropriate value of K. So whatever value of K we consider determines if we are underfitting or overfitting our model. What normally we do is we try randomly with various number of keys, and then we use we for each value of key we determine our error. What is our error? Our error is the average of how far our prediction or predictions are to the actual points, because it's in supervised learning we always have we always know the actual values. So after we make a prediction, then we try to determine distance between the predicted value and the actual value to get our error. So whenever you are doing KNN, this is true for all machine learning algorithms, but it's more true for KNN because of how it is. You have to scale your data. Otherwise, because it's using uh, the KNN, it assume all I think I've discussed this before. I don't know in which topic. It will assume all your data on the same scale. It will give you a lot of problem. So to locate the data point in multidimensional space, meaning you have more than one feature, all of them on different scale. For example, we have height and weight to predict a person gender. Height is on a different scale than weight, so we can't use the same scale. You have to do data scaling, and then we have to do uh, dimensionality reduction, meaning feature selection. We have a lot of features. We have too many features. KNN tends to not be able to work well. And then if you have this, if you meet all the Bala, can you meet everybody? Not the show how people are able to.
Ibrahim, can you make me co-host?
Okay.
Can you make me co-host so that I can?
Oh,
The one you see Shamsuddin only.
yeah. Let me stop sharing my screen first. I can't make you co-host like this more. Doctor, I can't make you co-host. I don't know why.
Ba kai ne Ibrahim ba?
Yeah.
Uh, so
Is there a limit to the number of co-hosts?
no, to cire wani daga co-host ɗin ko Shamsuddin shi wancan Shamsuddin Muhammad.
Oh, I'm not the host. That's why I can make you
Okay, to it's okay. Shikenan zan
Assalamu alaikum, doctor.
yau me da ni me co-host Shamsuddin din nan. Shi ma ba shi bane. Anyway, ku ci gaba bari na shiga ta host din. Let me log in back. Let me log in.
When I looked at it, I did not reclaim the host, so I think that's what happened.
Malam Saminu ne bari na yi rutin ɗinki out sai ya
Yeah, so next we look at linear models, and this is where we'll be doing, let me just play my screen. Kindly bear with me if you didn't get some of the mathematics. So linear models are a class of models that are widely used. They have been studied extensively in the last few decades. They have been widely used in the last few decades. Have been used extensively in the last few decades with roots going back 100 years. Linear models make prediction using linear function of input of features. Linear models generate a formula to create best fit line to predict unknown outputs. I'll explain this in the I'll come back to this. Let's first look at regression analysis. I already explained we are trying to predict a continuous value. Let's say like age, price, all of that. When you want to determine a set of predictors, forecasting, effect, trend forecasting. So when do you determine if to use linear regression? Depending on the capabilities, the quality of data you have, the computational complexity, and then comprehensible and transparent. I'll explain all of that, what they mean. Evaluating trends or sales estimate. When we want to, for example, analyze the prices of changes, I explained this. When you want to make any prediction has to do with price, assessment of risks and financial services, and every place that where the expectation is we have linear relationship between our dependent and independent variables. Okay, so this will clarify some of things I mentioned. So in linear regression, and not just linear regression, actually, in linear models, we use the equation of straight line, which is y is equals to mx plus c. You know what we do in machine learning? We have our dependent variable and we have our independent variable. If our y is our dependent variable, meaning it depends on the value of x. So we have two variables, y and x. The value of y depends on x. That's why we call our y our dependent variable and an x independent variable. So, and this our x, our independent variable can be our features. It can be only one feature or it can be multiple features, right? So we want to model the relationship between our y and our x. So one way to do that is using our equation of straight line, where we see our y is our dependent variable, our m, you remember, is the slope, and then c is our constant. So how do we do linear regression schemes to find the best fit line that represent the relationship between our independent variable x and our dependent variable y? So we have what is the equation? Y is the predicted or dependent variable, x is the input feature, one or many features, and then we have the slope, which is our m, and then we have our y-intercept, which is a constant, the value of y when x is 0. So this is generally the equation of straight line, and we use this in linear regression and all linear models. In fact, even the linear models, including the neural networks that we use, they are based on this equation of straight line. So how do we use this in linear regression? So first of all, we in machine learning, we start with our training. So given a set of data set that we know the values of x and their corresponding y, the values of our dependent and independent variables, the linear regression model, what it does is it tries to find the best values of our slope and our intercept where the line fits best. We try to draw a line that fits the highest number of points. So what is our goal? Is to minimize the prediction errors. What is our prediction errors? That is the distance between our data points to the line that we draw, the vertical distance between the actual points and the regression line. So we draw a line. I have a figure of how many. We have a line. We try to draw a line that cuts across all our data points. So the distance between our data points and that line is our errors. So what we want to do is to reduce the errors between that lines. And then, so how do we make our prediction? Once our model have determined the optimal value of our M and C, then we can use that to predict a new value of Y. Whenever we have a new value of, whenever we have a new value that we want to determine, we want to find a new Y, we know the X, so we have our slope and our intercept, and then we can get the value. For any given X, the model calculates Y using the land, slope, and intercept. So it already know the optimal values of which is the best for the model. So whenever you want to determine a new value, you want to make a new prediction, it uses the already land, slope, and constant, which is different from, if you remember, with how KNN operates. So what is our slope? It represents how much Y changes for 1 unit. Increase of X. When we have a positive slope, it means we have a positive relationship. As Y increases, Y decreases, also increases. So we have a positive relationship. They all increase at the same time. We have a negative slope, it means S increases, Y tends to decrease, or the other way around. And then our Y-intercept, our constant is the value of Y1 x is 0. It determines the regression line crosses the Y-axis. And then we can use our predictions to plot our regression line, alongside data point, help realize the relationship. We can see our relationship if it's linear or not, and this way we can determine if linear regression is the best model for us to use. Excuse me. So this is an example of if we have a positive relationship and a negative relationship. And this is what we try to do. We try to draw this line such that it is close to as many data points as possible. We can draw this line going this way or the other way, but we want it in a way that it's closer to most of the data points. So our prediction error, so whatever we are predicting will be along this line. So our prediction error are the distances between these data points and the line. So you see, this is our prediction error, all of this is repetition. So I will take us through how we can determine our slope. It's not absolutely important, but it's okay if you understand it. We have our multiple, you remember, we have our slope is equal to summation of x minus x bar. The product of that with y minus y bar all over x minus x bar squared. We'll see what is our x, what is our x bar, and all of that. So let's say we have a number of dependent variables, independent variables. This is our x, and then dependent values are y. Then when we find our mean of x and mean of y, it's our y bar. So what we do here is, for every point, we get the sum of each x minus its average. We multiply that to each y minus its average over the same thing here, squared. We get the sum. That's our slope. The line here is our y average, and then the line here is our x average. And then when you want to get this, you can do it in tabular form. It's easier. You see, you just have x, y. If you do this in mathematics, you remember we have our x minus x bar. Then you just fit it. Then we can have next our y minus y bar. we get the summation, then you just replace everything. This is mean x minus x bar minus y bar, this squared, the multiplication of this, then you replace, and then we determine our slope, and then we determine our intercept. So this is for the data points. So what happens in one of the, I've been talking about error, the distance between our data points and our slope, our data points and our slope. So what we do is we get the error, that's our error. So one way of determining how good our regression analysis is using, we have many methods, but one common method is the mean squared error, meaning the average square of our errors, all the errors that we have between the values and the actual and predicted, or the line, our regression line. So the mean square of that error, we get error. Always keep in mind, if you are doing regression analysis, we determine the error in terms of error, because you don't know the actual answer, so you are making error. If they ask you what is the accuracy, then you are doing classification. But anytime you are doing regression, you are determining your prediction error. Keep that in mind. That's how you differentiate between classification and regression. If you want to evaluate your model and you are thinking about error, whatever kind of error, then it's regression problem. If you are talking about accuracy, precision, recall, you are doing classification. So we can also determine using R squared. I will let you go over this. Okay. So this will be for our next class. We have logistic regression, Bayesian, and other models. Decision tree. I will not go over this. I'll stop. If you have questions, I take them. If you don't have questions, we go and look at what we have in our exercises. Okay. Any question? Let me quickly look at the chat. Okay, am I audible? Dr. Shamsuddin?
Yes, sir, you are audible.
Okay. So I will share my screen again. Okay, Naziru, go ahead. Ask your question. Okay, I need.
Assalamu alaikum.
Alaikum assalam.
Yes, sir. How can I determine that my prediction is good, or in terms of percentage?
Okay. For prediction, that's what I explained. You then get the percentage of how good it is. We normally talk about error. There are some, so it's error. What is a good prediction? Is a prediction that has small error. If your error is very small, then your prediction is good. If your prediction error is very large, then it means your prediction is not very good. So if you are talking about in percentage, then that is classification, not whatever. Even though we have some metrics that tends to, we have relative absolute, I think it's relative absolute error, it's in percentage. But normally, when we are talking about error metrics, we want it to be the smaller, the better. When you're doing regression analysis, we are talking about error, and then the smaller the error, the better. If you have zero error, it means all your predictions are 100% accurate. So that's how
Thank you.
that's how the relative absolute error works. How it's the relative your maximum number of errors, so it converted to percentage. But generally, in regression analysis, we use root mean squared error. You can explore more on root mean squared error. Any other question? So I'll go to the notebook because I did not explain this on the notebook, but what I have is in line with what you have on the notebook. And so I believe I explained everything within that notebook, aside from some of the visualizations done. You've done a lot of that. So we'll see, before I will go back to VS Code to see a very simple demonstration of what we do. So this is linear regression. Is the only thing I discussed. I did not talk about polynomial regression. Polynomial regression, linear regression assumes you have a linear relationship between your variables. If the relationship between your variables is not linear, then you have to use some other form of method like polynomial regression, like even neural networks. Even though neural network is based on equation of straight line, but it introduces activation function, which makes the model non-linear. So it's a non-linear method based on linear. It's a non-linear model based on a linear function. So, but I will not be talking about polynomial regression. Yeah. So we've discussed about determining the slope and all of that. What is the slope? What is that? So, okay, who is doing that? So you can determine the correlation. All of this is not necessarily a bit of pre-processing. So this is what is in the slide. Actually, why I decided in the text you have, why I decided to use those slides, it's because I think this is not that rich enough. We may need to update it. So let me just go to my VS Code. I will show you only one. Okay, this is only one example with the simple linear regression model. We have many other models that we can use. We can use the SVM for regression, which we call support vector regression in its own case, and many other models for regression. But for today, I'm only going to show you a very, very simple example based on what we have on our GitHub repo with a simple linear regression model. Why do I share my screen? So the data set in our you can see my screen, all right? The data set we have on our repo is about pumpkins, the price of pumpkin. Yeah, so if we do the pumpkins.head, this is what our data set looks like. We have city, from what city that pumpkin is, the type. We have a lot of missing values, the package, whatever that means, the variety, and all of that. So if there are some things that I just skipped from the code, but now let's just do take an example. So let's focus only one variety of pie. We have many varieties here. Let's just think about the pie type. So we just pick only one variety of the pumpkin. We have many of them here called pie type. If we plot it based on the day of year and price, this is what we have, whatever that means. So what we want to do is we want to take, this is a very basic example. We want to take this variety as our independent variable, and we want to take price. Among these features we have, okay, we have low price and high price. So, and then we want to use the price as our dependent variable. Based on the variety, can we predict the price? So I don't know if you have done that with the Shamsuddin. For all your machine learning, you will be using the library sklearn, and then if you don't have it installed, you have to do conda or pip install the sklearn library. I think to install it, you use scikit-learn, right? Pip install scikit-learn, and then we'll be using linear regression for this example. So from our sklearn.linear models, you import linear regression. We'll be looking at the error based on the mean squared error. So we import that from our metrics. And then, okay, I don't know if this has been explained. So when you are doing machine learning, I told you,
So Dr. Ibrahim, what we did previous our introduction is just introduction to what machine learning is. So don't make assumption like we did anything regarding regression. This is the first lesson on regression. So the previous one is just introduction, what machine learning and other stuff.
Yeah. So yeah, this is also machine learning. So in machine learning, normally when you first of all you have to install your libraries, as I've said, the sklearn library, and then we also have to normally what we do is, I explained how it works like in mathematics. You have your examples, you have the answers, the computer learn with that, and then when you want to know how well your machine works, then you compare with the actual values. So one thing we do is normally we do in machine learning is we have to divide our data set into training and testing. The training is part of the data set that we use in the training in where we give the model but the dependent variable and the independent variables, right? So the model learns with that. So we want to know how well our prediction is, how well our estimation is. We supply the test components, meaning we give it only the dependent variables where it does not have the independent variables. So it tried to make prediction based on that. Then we compare the predictions and the actual to know how well our model is. If whenever you build a model, you need to be able to know how good it is before you apply it in real life. So how do you know that? During building the model, you split your data into training and testing. Normally, you want to train with as much data as possible so that it has a lot of examples. When you are teaching your students, you give them many examples, many examples. Why? So that they learn all different scenarios. So that's how we do. So whenever you are splitting your data set, you pick most of the data set, depending on how large your data, on how large your data set is. You pick the training set and the test set. So we will be using this train test split. This we use it in all supervised learning, not just regression analysis. So this method, this function, do that for us automatically. We don't have to do it manually. So we have our X and our Y, if you remember correctly, right? We want to make our predictions. We have Y as our independent variable, which is the price. And then we have X, sorry for that, as our independent variable as the day of the year. So we want to predict, even in Nigeria, price of commodity are dependent on when you are buying them. Are you buying them the kakani ko the, what is the other one? During harvest when we don't have
Rani,
rani, yes, rani, normal rani, yeah. During the kakani ko the rani, it depends on that. So based on day of the year, which day it is, and which we have that in our data set, based on which day of the year, we predict the price. So our dependent variable here is day of the year. we have, that's what we have. And then we want to predict the price. We want to be able to predict the price. The prices changes, we don't know what they are. Every year it will be different. But what is fixed is day of the year. Day of the year is fixed. So that is our independent variable, and our y is our dependent variable. I remember our equation of straight line, right? Y is equals to mx plus c. So now we need to first know what is our y, what is our x, so that the model can be able to determine the slope or the intercept or whatever to learn with that. And then you remember what we looked at in our slides. So we determine what is our x and then what is our y from our data set. So, and then we need to determine 4 variables, 4 parameters. You are lucky, it's easy. You don't need to do them on your own. Your model already do them, so you can always do it. You can always use the method, the function that you have in your scikit-learn library. But you need to be able to do, we need 4 variables. Our x train, that means our x in training set, our x in test set, our y in training set, and our y in test set. If you think of this logically, right? We have our x as our independent variable. So when we want to do the training, we definitely need our x and y, part of it. Then when we want to test, we need our x and y also for testing. But when during tests, we don't give the model the y tests. We told that we only use the y test for what? Who can tell me? What do we use the y test for? Any guesses?
Evaluation.
Validation.
Yes, for evaluation, to know, because the model will predict those y. So if we do the prediction, then we use that to see how well the model is. So we need our x train, x test, y train, y test. Luckily for us, for everybody, now machine learning, it's easier. We use this method. X train, x test, y train, y test equals to use this train test split method. So you just have to pass your x and y, and here we already define our x and y from our corpus, from our data set, and then we tell it which portion of the data, of our entire data to use for training. So here we are we are telling it the test size. We are saying 0.2, 20% as test. It will automatically use 80% for training. This we can instead use, instead of test, we can use training size. If we tell it the training size, it will automatically use the remaining for that. It will use the remaining for testing. So that's what it does. So here we are telling it the test size of 20%. We are telling it, in other words, use the remaining 80% for training. And that's what we want. We normally want to use as much of the data set as possible for training, except if we have a very small data set, whereby if we want to do evaluation, we are left with only a few instances, then it doesn't make sense to use, then we maybe go for a maybe lower, a higher test size, maybe 40% or even 50%, depending on how large you want. But generally, for a normal data set, we can use up to 80% of that data for training and just the 20% for testing. And then when we want our split to always be the same kind of split, this is important. If we want to replicate our results, we put a number here. For our random set, we can put any number, so that anytime it wants to do the split, it will do the same kind of splits. So that if you want to try it with your friends, your answer will always be the same. You will not get different answers, because if you have different splits, you will have different answers. And then this is how we want to define our linear regression model. We can use any name here. We want to create an instance of this class. This class, linear regression, is part of the scikit-learn library that is used for doing the linear regression, fitting the line. So we want to create an instance of it. So we define it, we can give it any name, any variable name. Here we are using range, and it's a good convention to always use a name that when anybody looks can determine what we want. It's supposed to linear regression like this. Whenever you want to create an instance of this class, you use this. This is a class from the library. Then the first thing is, after we have the instance of our library, this is object-oriented programming, you have to fit your model. So how do we do that? We use this dot. So this range is our instance of the model. We put dot fit. This is instance of the linear regression model. Then we are fitting it based on our X train and Y train. So this we are doing, I should have commented this better. We are doing training. And then if it completes, it will give you this, meaning your model has trained. Then you want to do prediction. So you can just put any variable. Prediction is equals to your model that has already learned. Then you make a prediction based on your X test. So you make prediction of that. So this is for making prediction. Typically here, we've already built our model, but then we want to know how good our model is. To be able to know how good our model is, we have to make a prediction. This is what we are doing here. If we make a prediction, then we can use, we can determine the error. As I've explained, we determine error. We determine our error in regression models. So we are determining this is also variable name, just any name, mean squared error is equals to numpy dot the square root of your mean squared error of what? Your Y tests. This that I asked you, what are we going to use it for, that you told me, and then the prediction that you make. And then you just print your what do you call it? You print your prediction error. Our prediction error is 2.775. And then this is not necessary, but this try to get the absolute error in terms of percentage, meaning it's 17%, smaller the better. But this really doesn't tell us much. What we need is our mean squared error. Whenever you are reporting your error results for regression analysis, you report your mean squared error. But sometimes people are fixated on getting accuracy. So you can get the relative percentage of the largest amount of error that you get in your prediction, and the smallest, then you get a percentage of that. And then we can get our model determination using this. And then here we plot. Okay. Can you see my screen? No, right?
No, we cannot see.
No, sir.
Who took over my screen? Somebody stop sharing my screen. I don't know what happened actually. So I explained about what we want to do is to get the best line that is closest to most of our data points. So this we are just plotting is scatter plot of our X test and our Y test. And then we look at this line. I don't know if you agree that this line is drawn in a such way that it's close to most of the data points. So I will stop sharing my screen. I don't know, I will take more than 30 minutes for this session and take question. You have all the slides of what I discussed today already shared in your Telegram channel. So any question? So the Shams, don't over to you.
It's okay if you are done, then
Okay, so any question? No question? So have a very good day. A sha ruwa lafiya.